All right, good morning. Here we are yet again for another lovely session of MENG 3310 Fluid Mechanics. So today we're going to finish up our discussion from Chapter 6 of the text, looking at the Navier-Stokes equation. Then in following lectures on Wednesday and Friday, we'll be looking at dimensionality and similitude, which is always a fun topic that students have to pound their head against the wall before they figure out, but we'll get through it. Okay, So anyway, our topics for today, I want to discuss stress-deformation relationships, develop and apply the Navier-Stokes equations, apply the Navier-Stokes equations, and discuss steady flow between parallel plates. That is my agenda for today. So let us look at stress-deformation relationships. If I can manage to write a D. Stress-deformation relationships. All right, so for incompressible fluids, we have a stress relationship like this, or distribution like this. So, consider an element inside a fluid. There will be if I consider a small differential element of fluid, a small cubical differential element, y, x, and z axes, there will, if I could, and again, this is going to be a small differential element. Oh, maybe I'll draw it in orange. So in case you can't tell my poor art skills, this is meant to be a perfect cube, but best laid plans of mice and men, etc., etc. Okay, so this is a small differential element, and we'll consider three stresses on it. On this face, you would have a, I'm going to call a sigma YY. On the vertical side, I would have, on the top element, or in the XY plane, I would have sigma ZZ. Sigma ZZ. And then the X, I would have a stress sigma XX. Sigma XX. All right, and then, but the relationship between these for incompressible fluids will be that P, the pressure, is equal to negative 1/3 times sigma XX plus sigma YY plus sigma ZZ. Okay, so this is the stress on a small differential fluid element. Now, let us look at this in some more detail. So let's see what this actually means. So we have a fluid, and this is basically the stresses that we'll be looking at. And let's take a look. So for a Newtonian fluid, and this is really the definition of a Newtonian fluid, for a Newtonian fluid, you may have heard of the difference between Newtonian and non-Newtonian fluids. You can find some great videos on YouTube searching non-Newtonian fluids, things like that classic cornstarch solution and things like that. But if you're interested in seeing some interesting things, did I really just say interested in seeing some interesting things? If you're looking at, if you're interested in that, just look up non-Newtonian fluids on here. Okay, so Newtonian fluids, but we're sticking with the simple things. For Newtonian fluids, fluid stress is related to fluid strain. And they're related by this function, or this set of functions, related to fluid strain. So sigma XX is equal to negative P plus 2 mu times d, the partial of u with respect to x, sigma YY is equal to negative P plus 2 times the partial of 2 times mu times the partial of v with respect to y, and then sigma zz is equal to negative p plus 2 times mu times the partial of w with respect to z. And these are our normal stresses here. And actually, let me just comment, add a little note here. The stress is linearly related to the strain. Is linearly related to strain. And this is very similar to linearly elastic materials. You can find very similar equations in any mechanics of materials textbook to linearly elastic materials. If I can manage to write a Y, linearly elastic materials. All right, now look at the shear stress. So these are, actually let me kind of comment on this. This would be my normal stresses. And I would also have shear stresses. And I would also have shear stresses. And these stresses would be as such. Tau xy is equal to tau yx is equal to mu times the partial of u with respect to y plus the partial of v with respect to x. And tau yz is equal to tau zx is equal to mu, and you can probably see where this is going, the partial of v with respect to z plus the partial of w with respect to y. And the partial of, and then the tau zx, well, this is equal to tau xz, and this is equal to mu times the partial of w with respect to x plus the partial of u with respect to z. Yes?
Should the second one be tau yz?
Oh, thank you. Sorry about that. That should be yz, yes. Zy, actually, yes, sorry. Little typo there. Okay, so let us look at the Navier-Stokes equations. Okay, so the Navier-Stokes equations. So the basic idea with Navier-Stokes equations, by substituting in the stresses into equations of motion, the Navier-Stokes equations can be found. So in the x direction, we can have something like in the x direction, and I think I'll just write out one of them. You can find the rest of them in your course text, but the basic idea is something like this. You'll have rho times the partial of u with respect to t plus u times du dy, or the partial of u with respect to y, plus the plus w times the partial of v with respect to z is equal to negative partial of p with respect to x plus rho gx plus mu times the second partial of u with respect to x plus the second partial of v with respect to y plus the second partial of u with respect to z, or partial, sorry, of w with respect to z. Okay, so as you can imagine, this gets a little tedious to write all these out. I will simply say there's going to be one for the x direction, there'll be one for the y direction, and one for the z direction. But what I really want to get at is the basic relationships here. So there'll be three sets of equations, one for the x direction, one for the y direction, one for the z direction, and this differential equation sets up the relationship between velocities, your stream functions, your stresses, etc. Or actually your strains and your velocities. So that's the basic idea. Okay, so I could write all of these out, but this is the basic idea here. So for the full long form of all of these, I would consult your course text or many online sources. I just they get a bit tedious to write all of them out mid-lecture here. Okay, so I think I want to go directly to some examples. Maybe I think that might be a better use of our time, writing out a few example problems. So, example. Let us look at the laminar flow between parallel plates. Laminar flow between parallel plates. So say we have something like this, and so here we have two plates, one plate here and one plate here. Now, we looked at something similar when we first considered the definition of strain, where we had one of the plates moving, but that's not going to be the case here. We're going to have both plates stationary, both plates at rest, but then simply a fluid flow occurring within them. And I'm going to find H and H as such here, H and H as such here, and G is going to be going downward. I'll have G, the gravitational acceleration, pointing downward, and U, the x velocity, will be going to the right. So we'll have a very simple XY system here. And so I can basically, in many of these cases, in many of the problems, what you'll see in the textbook and what I introduced to you a bit before here is the full Navier-Stokes equation. And in the full form, the equations can be quite long and quite complex. But as you probably got the hang of by now, in most systems, those are your general equations. But in most real systems, or in most problems and things like that, on whether they're homework or exams or design examples in the real world or whatever it is, in most cases, not all cases, but in most cases, a lot of those terms drop away. You may have some complex systems, like you were doing three-dimensional fluid analysis, computational analysis, that sort of thing, that you would have to use the entire thing. But in many examples or in many applications, a lot of those terms are going to drop away because different terms are zero. And this is an example of that here. So let's consider this. So if I consider this, so particles are moving, move along plates parallel to the x direction. Parallel to the x direction. So v is equal to w is equal to the partial of u with respect to x is equal to the partial of u with respect to t. And it's steady as well, and this is all then equal to 0. So, looking at this, so v is equal to w equals to the partial of u with respect to x equals the partial of u with respect to t. All of these are equal to 0. Okay, so then the Navier-Stokes equations, and I'll reference the three equations, and again, the first one, x, y, and z. So the equations reduce to well, in the x direction, we end up with 0 equals the negative partial of p with respect to x plus mu times the second partial of u with respect to y. Everything else drops away to 0. In the z direct or in the y direction, I'm left with 0 equals the negative partial of, and that is a x here, sorry about that. 0 equals the negative partial of p with respect to y minus rho g, and 0 equals the negative partial of p with respect to z. So the z direction, this is the z direction Navier-Stokes equation. And then I can take I can take the y direction, bring this down here, and solve for this in a different manner. So I bring this down here, I can get that rho g, is equal to negative partial of p with respect to y. And then if I bring this over here, rho gy, or rho g dy equals negative negative dp. I take the integral of both sides, and I get that rho gy plus c is equal to p. Rho gy plus c is equal to p. Or p is equal to negative rho gy plus some constant, which would be a function of x. Some sort of function of x. Here. Okay, so in other words, the pressure is hydrostatic in y. It would have to be some sort of function of x. Okay, so continuing along. I'm going to do a similar thing for this equation here. I'm going to let me just call this equation 1, equation 2, equation 3. So again, this from 2. Okay, now 1 becomes, well, I can then go and say, okay, the d squared u over dy squared is equal to 1 over mu times dp dx. And then I can take the integral of that. here. Oh, something like this. So I will get the, then the first derivative of u with respect to y is equal to simply 1 over mu. Oh, and this is times here. Let's do the integral of dp dx again, times y, and this was integrated with respect to y here, plus c1, and at the end of this, when I integrate this again, I get u equals 1 over 2 mu times the partial of p with respect to x, y squared plus c1y plus c2. And if the two plates are fixed, u equals 0 for whenever y is equal to plus or minus h. So we know at the surface of the fluid, or the surface of the plate, the fluid velocity has to be 0. So I can use that as a boundary condition. And the velocity distribution then becomes, or I should say, therefore, c1 equals 0, and c2 is equal to negative 1 over 2 mu times partial of p with respect to, actually that should be an x here, sorry. Partial of p with respect to x, partial of p with respect to x times h squared. And then the velocity distribution becomes, and I think there may be some slight, I need to dig into this some more, there may be some slight issue with that integration there. But the velocity distribution then becomes u is equal to 1 over 2 mu times the partial of p with respect to x times y squared minus h squared. So in other words, we have a pressure gradient. That's an x there. We have a pressure gradient along x. If I can close that parentheses first. We will have a pressure gradient along x here. A pressure gradient along x. So in other words, we have something like this. So there may be a pressure gradient like so, starting out at 0 at the edges, and then in a parabolic fashion going like this. So we see that u, well, if there may be a pressure gradient if there is any kind of variation in x, but at a given x value, if I look at just a single x coordinate here, this x coordinate here, the velocity will depend on this here. Will depend on the y and the h here. Basically, y being the exact coordinate and h being the actual dimensions of the pipe. All right, so we're not quite where we want to be yet. We still have some work to do. For a unit width of W, W equals 1, and flow rate Q, well, Q is going to be equal to the integral from negative h to h of u dy. of u dy, and this is then equal to the integral from negative h to h of 1 over 2 mu times the partial of p with respect to x times y squared minus h. Basically, I'm integrating this thing with respect to y, dy here. I'm integrating the previous equation with respect to y here. And I will get then that q is equal to negative 2h to the third over 3 mu times the partial of p with respect to x. And then I can say let delta p be the pressure drop length L. So when I say a pressure gradient, this delta p, this dp dx, or this partial of p with respect to x, what do I mean by this? What I'm saying is, as you go along the length of a pipe, the energy in that pipe will go down. The pressure energy, the velocity energy, whatever you want to describe it, the energy in that pipe will go down. So we have discussed this before when we've labeled the concept of head losses, but this is the first time we're actually seeing how you might directly calculate it. And it comes directly from the Navier-Stokes equation, or Navier-Stokes equations, from these base principles. So when you, this dp dx, I want you to, maybe you don't quite get what this is saying, what this means, but in other words, if I measure the pressure here, I find that the pressure here is slightly greater than the pressure over here. If you have very precise and exact equipment, you can actually measure this even over a course of a couple feet if you had precise enough equipment. And again, the assumptions of this are going to be linear flow, Newtonian fluids, etc. But when we say a dp dx, I have a x-coordinate here, I have an x-coordinate here, and there is a drop in pressure along this length. We are losing pressure due to viscous forces as we go along. Along length L, so I'm going to define this as this, and so delta P over L is equal to negative partial of P with respect to X, and sorry for going through this pretty quickly, but we have a lot to cover today. So again, delta P over L is going to be equal to the negative P divided by delta X, or divided by dx, and so then Q is going to be equal to 2h to the third times delta P divided by 3 mu L, or finally my, if I say let mean velocity be V, so the flow rate is this. If I let the mean velocity be V, well, V then is going to be equal to h squared delta P over 3 mu L. Or we could also work this as, let's see, if we solved this for delta P, I could also have delta P equals 3 mu L V divided by h squared. And we could easily turn that h into a diameter as well, if we wanted. Or I guess, well, this is assuming parallel plates, but that's the basic idea. And then at y equals 0, the max velocity is going to occur. So y equals 0 defined as the middle coordinate. And this is going to be u max is equal to 3 halves v. U max equals 3 halves v. All right, so U max equals 3 halves v. So this here, I probably should have labeled this better. This is our velocity profile at a given x value. So again, toward the walls of the pipe, you're going to have 0 velocity. toward, and so at the top and the bottom of the pipe, or in this case the plate, you would have zero velocity. Then you have, as we've derived here, you'll have a parabolic relationship, and then right at the peak, or right at the center, you'll have the peak velocity. So we see here that at a given cross section, all of the fluid in a pipe is not traveling at the same velocity. There is a core, or there's a distribution. There is a distribution of velocities where right at the edge of the pipe, the water is literally, or the water or whatever fluid, oil, whatever it may be, right at the edge, the fluid is literally stationary. It's not going anywhere. At the center, it is, actually, maybe I can draw this out a bit more over here. So, velocity distributions between parallel plates. You'd have to do a different derivation for a pipe. There you would have, you'd have more of a cone type thing rather than a 2D thing. But if I look at between these parallel plates, so again, I have my plates here, and again, all of this is occurring at a single x coordinate. So it's this, what I'm drawing is a velocity profile at a given coordinate. So some x value, and this is going to be the velocity profile at a particular x coordinate, where x is along the length here. At a particular x coordinate. So, at the, down here, at the walls of the pipe, I have zero velocity, v equals 0, although, actually, let me say u equals 0 to be consistent. U equals 0, u equals 0. Then, I would have at here, at the center, u max equals 3/2 v, where v is not the y velocity, it is the average velocity. Or, you know, maybe I could call it v bar or something like that. Let me just call this v bar, v bar. I like that a little better, actually. So v bar, maybe you could call it v bar if that's not too confusing. And then we would have a parabolic relationship developed kind of like this. And then, so all the way along here, you'll have at any given height, or at any given distance from the center, you'll have a different x velocity. And I apparently can't draw parabolas. But then, somewhere along the line, you would have a v bar. So at a particular height, you would actually have the average velocity. It is really just the integration, or the mean value theorem applied to the, it's the mean value theorem applied to the u distribution. All right, I have one other example problem I'm going to work through if I have time. Okay, and this is problem 6.69 from the text. .69 from the text, and given a particle moves horizontally, if I can write, horizontally along a streamline, along a streamline that corresponds to the x-axis. And so this is, I will say this is plane, two-dimensional flow, so plane flow, not P-L-A-I-N, but P-L-A-N-E, two-dimensional flow. And that u is equal to x squared. And also that this is we have an incompressible flow field. And I want to find A, the rate of change of the v component of velocity with respect to y, of the v component of velocity with respect to y, B, the acceleration of the particle, and C, the pressure gradient in the x direction. In the x direction. All right, so let's work through all these. Part A. From the continuity equation, let's see, the partial of v with respect to x plus the partial of v with respect to y is going to be equal to 0. Now, when u is equal to x squared, we will have the partial of v with respect to y is equal to the negative partial of u with respect to x is equal to negative 2x. Then I could bring this over here and say dv is equal to negative 2x dy, integrate both sides, and I would get that v is equal to negative 2xy plus some constant, which would be a function of x. And then but to get rid of this constant, I can say that x-axis is a streamline. If the x-axis is a streamline, therefore v equals 0 along the axis, the y velocity here, the axis. So in other words, when I say the x-axis, what I mean is when the x-coordinate is 0, the velocity is 0 along axis. Therefore, f of x, that constant, collapses to 0. So v then is equal to negative 2xy. Again, where I'm getting this is when I say the x-axis is a streamline. That means that if I release a particle anywhere along the x-axis, it's not going to go up or down in the y. It's just going to happily drift along the x-axis to some. It's going to happily drift along the x-axis with some variable velocity. Then for part B, well, I can say that ax is equal to u times the partial of u with respect to x plus v times the partial of u with respect to y, which comes to x squared times 2x plus the negative 2xy times 0, or just equals 2x to the third. And then ay is equal to, maybe I'll just underline that, AY is equal to U times the partial of V with respect to X plus V times the partial of V with respect to Y. And this is equal to X squared times negative 2Y plus negative 2X, or negative 2XY, negative 2XY times negative 2X, and this is equal to 2X squared Y. Or just equal to, sorry, not negative 2X squared Y, just 2X squared Y. And if I then, if I want to look at the Y-axis, say I want to look at the Y-axis, or actually the X-axis, sorry. Consider the, we want to look at that streamline along the, we want to look at the particle along the X-axis, the streamline. So consider the X-axis. Well, along X-axis, Y equals 0, so this term goes away. Therefore, AY is equal to 0. So the only acceleration component remaining is in the x direction. So the acceleration vector then is simply 2x to the third times I, our vector, our unit vector in the x direction. Then part C here. I will reference an equation in the text that you might want to consult, equation 6.127a, with gx equals 0, one of our equations in our discussion of Navier-Stokes, negative 1 over rho times the partial of p with respect to x, plus the times the partial of p with respect to x, if I can, plus mu over rho times the second partial of u with respect to x plus the second partial of u with respect to y. And then 2x to the third. So this equals, this is again, ax is 2x to the third equals negative 1 over rho times partial of p with respect to x, which is our pressure distribution that we were looking for earlier, that we're looking for, plus mu over rho times, well, this is just going to be 2 plus 0. If we take these and take the derivatives of them, it'll actually just be 2 and 0. And so finally I can get that the partial of p with respect to x is going to be equal to 2 mu minus 2 rho x to the third, as such. And that is our final item on the Navier-Stokes equation. All right, I know that was a lot. I know I went through that very quickly, but wanted to get through this material and finish it up so we can get on to dimensionality and similitude on Wednesday. As always, thank you. I'll see you all later. Take care, and as always, thanks for watching.